So this idea of chemistry, chemical understanding, and chemical intuition. As a chemist, somebody who is trained as a chemist, that's kind of how I think about things, is what are the atoms, how do they bond to one another, and what sort of molecular shape or larger three-dimensional structures that create. As an engineer, what you typically think about is, okay, let's assume we have the material, how do we process it into the right form? The challenge with that is when you go through those processing steps, that influences the chemistry. And it changes those molecular structures and how they bond. And a lot of what we do with self-assembly and supermolecular interactions and those types of modes of controlling structure, they're not really compatible with processing. You need ways that are lower temperature, things that can be done under ambient conditions, things that don't require a 500-degree oven or a blast furnace or massive amounts of pressure. And essentially what we're developing are ways where under ambient conditions, 30, 40 degrees Celsius, room temperature perhaps, you can apply just a little bit of pressure, heat, light, some small amount of stimulus, and you can shape and mold that material without disrupting any of the self-assembly aspects that we worked so hard to maintain. The three most relevant and important aspects of our research for industrial applications right now are focused on sort of the three-letter acronyms we have. We have NCTs, we have XNPs, and we have PAEs. NCTs are sort of the biggest hit that we've had. It's sort of what put our lab on the map. It's the idea that nanoparticle self-assembly has been a thing for several decades. People have known how to take tiny spheres of all sorts of different materials and program them to spontaneously build up into some sort of ordered lattice structure by virtue of how they interact. None of those methods are scalable. The best methods can maybe make 2D planes, like a thin coating on something that's wafer scale. But nobody's been able to make large macroscopic three-dimensional structures. It just has not worked. They're too expensive, they're too fragile, they simply can't achieve that, as fantastic as they are. What we've done with NCTs is we've now developed a much more scalable route. So we can actually make potentially gram-scale quantities of things where we can self-assemble an object. It has those same nanoparticles. They're organized into complex three-dimensional arrays, but then we can process, mold, and shape them into physical objects you can pick up and hold in your hand. Where we're going with that is, again, further scalability, making it so it's not just maybe a millimeter or centimeter sized object, but something larger. But also trying to figure out ways to incorporate it into existing materials. So we don't want to have to reinvent the wheel for every single device, application, or material that somebody might want to use our NCTs for. We'd like to be able to say, our NCTs have this particular optical or electrical or mechanical property. We're going to take a small amount of it and mix it in with the material you've already got to make it better. So the idea is not to make an incredibly expensive material that is built entirely from scratch, but to make a key active component out of these NCTs and then add it to a pre-existing pipeline of materials that companies or other researchers would want to use. And so an NCT, just so you have this, an NCT is a nanoparticle coated with what's called a polymer brush. So basically you have a particle, and then coming off of the particle surface, a whole bunch of polymer chains. It's literally a brush. It has hundreds or thousands of these pointing into solution. We didn't invent that concept. What we did was we figured out how to modify those brushes to have those supermolecular interactions that allow the particles to talk to one another. So in a very simple term, we basically put a fuzzy coating on the particle, coated with a smart glue that allows particles to, when they bounce into each other in solution, they can recognize in one another and say whether or not they should actually form a bond. This allows us to basically synthesize a large batch of them, shake it up in a solution, and they spontaneously organize into something that is much more complex and much more ordered than just a random arrangement of particles.